So in our last video, we were talking about conductors and insulators. So we were saying that, for instance, for a metal conductor, they allow charge to pass through them very easily. Is what makes them a good conductor for, conducting electricity. But that also means that if you want to build up a charge on them, you have to insulate them so they have no way of passing on that charge to the ground and discharging. Whereas for an insulator, they have no free electrons. They can't conduct electricity. Therefore, that means that if you can manage to strip some charge from them, strip some electrons from them, or equally to put more electrons on them, say by rubbing a cloth on them, that's an example we're going to use, then that means you can actually build up a charge on them because the charge won't go anywhere. It has no means of escaping. That means that, say, for this boot as I'm showing, if we say rubbed a cloth on that or something, we're able to deposit electrons upon it, we would build up a negative charge on this part of the boot. So the upshot of that is that this means that we can actually build up a charge on an object and experience the electric force on scales far larger than that of individual particles. And as I was saying earlier, a good example of that is static electricity. So if we go back to thinking about what we were saying about charge and forces in our first video, we were saying that really we were illustrating that with protons and electrons, etc. These fundamental particles that have the charge associated with them, these fundamental charges. But really we don't need to think about that as a way of demonstrating electrostatic force, because we can do it on much larger scales. We've all seen static electricity. It's something you can see with large objects. This is an example of, it's a very complicated example of static electricity, but this is the levitation of a ball using static electricity. The idea being this gravitational force downwards on this ball, but at the same time, well, that'd be its weight, excuse me. At the same time, there is electrostatic forces here because there's been a charge put on these objects. Therefore, they're repelling each other and allowing it to hover, and so there's much more complicated than that, but that essentially is what's going on there, using static electricity to allow this ball to float. And there are plenty more examples of that. So for instance, we were thinking about rubbing a polythene rod with a neutral dry cloth. So that means the cloth itself here is not charged, but we rub this rod, or basically this plastic rod, with this cloth. What happens is that the rod will gain electrons from the cloth. So we rub this cloth on this rod, and what happens is that this rod will gain a negative charge on it, say here, and this rod will gain a positive charge on it because it has lost electrons. Now, we're not so interested in the cloth, but we are interested in the rod because we now basically built a charge on a rod. And you can, there's many demonstrations of this, and we'll talk about one here, but there are also others. But let's just do this now. So for instance, doing this, putting this negative charge on this rod, because what's happened is we've essentially just transferred electrons. So electrons are really going to be most of the way we think about charge in this. The idea that you gain or lose electrons, and that's what gives you a net charge. And so doing that, basically we've swapped electrons from this cloth to this rod, building up a negative charge. Remember, electrons are negative, so if you lose them, you get a positive charge. If you gain them, you get a negative charge. What that's going to do is leave our plastic rod with a net charge. It will also leave our cloth to be charged, but we're not so interested in that.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.